TI9. So let's draw the picture. And you might have noticed that the same thing happened. Let's see here. So, okay, what have we got here? Y equals 0, 0 equals 0. Yeah, so the first three planes here, the first three surfaces are planes, and they're all parallel to the x-axis. That's the first thing you notice. So y equals 0, z equals 0, and 3y plus 2z equals 6. There's no x's anywhere in any of those. So they're all planes parallel to the x-axis. And let's just kind of get that down first. So y equals 0 and z equals 0 are easy. And then 3y plus 2z equals 6 is going to be kind of like this. So we've got this kind of triangular prism kind of looking thing. Is that cool so far? So we got, yeah, okay, cool. All right, good deal. So, all right, now we just have two more surfaces, and really, in fact, we don't even have to draw the whole surfaces. We just have to draw how do these surfaces relate to this triangular prism, right? And so let's look at the first one, x equals negative y squared. Well, keep in mind this is the x-axis. If you have x equals negative y squared, in particular, that's some surface where x is negative. So, I don't know, it's going to be some sort of I could try to do a decent job of drawing it perhaps, but whatever. It's some surface back here. And so it's going to chop through that triangular prism in some way.
Okay, so I have a question about that specifically. Because, like, when I drew it, so I just kind of looked at it in terms of take, in the xy plane, it's like a negative parabola.
Yeah.
On the.
Yeah, no, you're right.
Flip-flop. So, like,
yep.
How do you.
No, my picture's bad. I mean, you're right. I mean, it goes through the origin, for example, and I didn't draw it that way. But I'm just trying to draw it that. I mean, qualitatively, what matters is that it's x is negative. And if you want a realistic picture, okay, that's a taller order, right? And I claim we actually don't really need it.
Okay.
So qualitatively, I claim that. Give me another 60 seconds, and then if you want me to draw a better picture, I will.
No worries.
Okay.
I just like really couldn't.
Yeah. So, by the way, when you're drawing pictures, I mean, one good thing to do is, don't set the bar too high unnecessarily. In other words, realize what the picture is supposed to serve. The picture is supposed to serve to help you to be able to write down what you need to write down. And if your picture, however bad, can do that, hey, the picture was good enough. And don't get bogged down in shading and stuff that it's really, really difficult to do without technique and lessons and tools. Okay, so let's look at the other one. This last surface is x equals 1 plus z squared. So yeah, it's going to be some sort of a paraboloid or parabolic kind of thing. It's a surface, but check it out. X is positive. That's the big moral there. X is positive, right? So sure, maybe it looks kind of like this or something, and it's got this kind of a bent shape to it, but that doesn't really matter. What matters is that, well, you've got one surface that's cutting way over here, and the other surface is cutting through the triangular prism way over here. So in some sense, qualitatively, this is what our guy looks like. And so let's see if we can't make it work with this, and if we can get our answer out of this picture, then we won't worry about the fact that it's a bad picture. Okay, next observation. I note that this shape has a very convenient projection into the YZ plane. Right, its projection into the YZ plane is this little triangle. Now, its projection into the XZ plane is weird. Its projection into the XY plane is weird because of these curved shapes and everything. But if you just take this whole thing and just kind of smash it, well, I got to, angle, smash it into the YZ plane, it's just that triangle. So I'm going to use this projection idea and take advantage of the fact that if I restrict my attention to what's it doing in the YZ plane first, and I'll worry about the X bounds later, right? By putting Y and Z on the outside like that, all I really have to do is ask what's the range of values of Y and Z. Forget about the solid. I just want to know the range of Y and Z on that projection.
Okay, so
cool?
Because you're switching it to the YZ plane.
That's right.
On the outside.
Yes, that's right. That's right. Exactly. So, all right, well, let's see. This is 3 up there, and this is 2. So it looks like Z goes from 0 to 3. And for any given value of Z, I got to figure out what's the corresponding value of Y. Well, I mean, clearly Y starts at 0 and goes to something, so Y starts at 0. Put that there. So this Y2 over here is, well, Y and Z relate by way of an equation that is, well, I've got that's the equation of this line, 3Y plus 2Z equals 6. Just solve for Y. And in 3Y plus 2Z equals 6, and of course Y then is 6 minus 2Z over 3. So that's what goes here. Is that cool? So I'm 2/3 of the way done, and I haven't even, it seems like I've just kind of worked a double integral problem really so far. So the last thing where you really do have to have the three-dimensional picture is to figure out what's the range of values of x. So we're going to pick now, suppose we've got a y and a z chosen, and I need to know what's the first value of x, and then what's the last value of x. In other words, I need to solve for x on that back surface, and then I'm going to need to solve for x on this front surface. Good news, it's in the statement of the question. Both of those surfaces, x is already solved for. So, yeah, negative y squared, that's right, and then 1 plus z squared over there. And then let's see, what was did we have an integrand? Oh, it's just the integrand was just called f. And of course, we can't evaluate this because we don't know what f is. But the problem was just to do this phase 2 part of the problem, and there it is. So again, this is not what the back surface looks like, and this is a not particularly great representation of what the front surface looks like. But all I really needed was to know that they were there, and that qualitatively this is what the thing looks like. I mean, it would have been problematic if these two surfaces themselves might have crossed and intersected, and then you wouldn't have necessarily this triangular projection. Something really terrible might happen, but it didn't. This one's way over there. This one's way over here. And they never intersect. They're not in anybody's way. They're just over there, and so let's do that. Is that cool?
It is. It's a lot. Yeah.
Yeah.
It makes a lot more sense.
Good. Yes.
Oh no, no, I'm just.
Okay. So let me. I'll stop this one here and let's go on to the next one.